I hope I'm audible and visible. Okay, so today we'll be starting with dynamic programming part 2. And these are the things that we will cover in this lecture. That is LIS, LCS, LRDP, and two problems of buy and sell stock. Now let's start with our first problem from subsequence DP, which is longest increasing subsequence. Now, what do you mean by longest increasing subsequence? First of all, what do you mean by subsequence? A subsequence is a part of an array where the relative ordering of the elements doesn't change, but they need not to be continuous. Suppose in this example, 3, 10, 20 is a subsequence, 3, 1 is a subsequence, likewise. So we need to find the length of the longest increasing subsequence. In this example, as you can see, 3, 10, 20, the length of the subsequence is 3. So that is the longest increasing subsequence. In this, as you can see, the entire array is decreasing. So the longest increasing subsequence length will be 1, that is taking just a single element. Now, what can be the approach of finding this? So we need to explore all the possibilities, like we need to explore all subsequences and track which one can be the maximum. So whenever this fact of exploring all the possibilities come, we take recursion into account. Now, there are the first thing that you need to think about a recursive function is that what will be the state of the recursion? Okay. Now, when we are calculating our longest increasing subsequence, so what are the things that we need? We need two values. That is, what is the value of our current index and what is the value of our previous index. Why do we need the previous index? Because we need an increasing subsequence. So if we don't know what value we have taken previously, we will not know that what if the value that I'm taking is greater than the previous value or not. So the state of the recursion will have two changing parameters, that is I, that is my current index, and the previous, that is my previous index. Now, initially, when we haven't taken anything into our array, we will initialize previous to -1. Now, why do we do that? Because whenever we are like not taking anything in our array, we can take any value, however big the value can be. Since we haven't taken anything in our subsequence, we can take any value. Okay, so this is the state of our recursion. Now then comes the transitions. So every time you think of any recursive approach, try thinking like this way. You first think of the state, that is, what is the changing parameters, and then you think of the transitions and what answer do you need. Okay, then you think about the base case. Now, let's deal with transitions. Now, what are the transitions that we can have? Suppose I am having an array 3, 5, 1, 6. Okay, so in this array, I initially my previous pointer is pointing to -1. So I can take my first element. So if I can take my first element, then I am increasing the length of the subsequence by 1. Okay, so if I'm taking my element, but if I'm taking the current element, then my length is increasing by 1, and then I need to see for the rest of the array that what are the elements that I can take from rest of the elements starting from I+1 index. Okay, now since we have taken this ith index, this becomes my previous value because we have already taken it into consideration. So when we are dealing with the take condition, we recursively call our function by updating our previous value to I and the next value to I+1, because we'll be exploring from I+1 value to the end that what are the possibilities, that what values that we can take. And since we have taken 3 as our element already, so we update the previous value. You see, we have taken previous value as I. So what is the condition that I can take my previous value? You cannot always take a particular value. Suppose you have taken 5 into consideration, then you cannot take 1 in your array. So what are the conditions that you can take a particular element? So when I haven't taken anything in my array, I can always take that element. So if my previous is equals to minus 1, that means my subsequence is empty. So I can take anything in my array. This is the first condition. Now, what can be the second condition? That is, if my current index's value is greater than my previous index's value, which is the condition for to get an increasing subsequence, of course. So another condition will be if my current index's value error of suppose I is greater than error of previous. Only in these two cases I can take my current element. Okay. Now there is a choice that I can not take my current element also, because whenever my previous is pointing to 1, I can choose if I'm taking this 3 if or I'm not taking this 3. Okay, like if you're taking this 3, you will get a subsequence of 3, 5. If you're not taking this 3, you can start from 1 and then you can get a subsequence of 1 and 6. So for each and every element, you will have two decisions. That is, either you can take it or you can not take it. So for taking, we have seen that these are the two conditions when we can take an element. So what will be the conditions of not taking an element? There are no conditions, right? Because you can, it's completely up to you that if you can take an element or not take an element. So for not taking, we are not increasing the length of our subsequence because we are not taking that particular element. We simply call it with the next element's value and the previous remains the same because we haven't taken any element. So this is the transition. Now, what do we need to return? Okay. This is the thing that what we need to return. We need to return our longest increasing subsequence. That means we need to return the maximum length. So what do we return? We return the maximum of take and not take. So we explore all the possibilities having by taking this particular element, by not taking this particular element, and then we return what is the maximum length that we can achieve by having these two decisions. Okay, so this was the transition portion. Now, what will be the base case? Because the recursive function needs to end somewhere, right? So, what will be the base case? The base case will be if you're reaching at a particular index which is out of bounds. So we are starting from the 0th index and we are progressively increasing our index by I plus 1. So sometime if our index becomes equals to n, that is we have already reached out of bound of our current array. So in that case, what do we return? We return a 0. If I equals to n, we return a 0. Now, because if we have reached this value, there is no other option. You are not increasing your length of the subsequence. So you just return a 0. So this is the thing for the recursive function. You see here the implementation, as you can see, we have taken a vector a, and whenever this is the base case, whenever we are reaching a dot size, then we are returning 0. And then there are two decisions that we can take or not take. So, and finally we return the max of the two. Okay, so this is the recursive approach. Now, what is the time complexity? Since for each and every element, we are having two choices. Okay, either to take it or not to take it. Since we're having two choices, the time complexity is 2 to the power n because there are n elements and for each element we are having two choices. Now, what is the space complexity? That is big of n because we are using a recursion and as you know, recursion always takes an extra stack space. So that is big of n. Now you see the time complexity is really very high. Now, how can we optimize it? While you are implementing the recursive function, you will see there are certain states which are getting repeated. Okay. Now, suppose you have already calculated the value of 1, comma 0. Okay, you have already calculated this value. Now, when you are exploring some other decisions on your recursion tree, you find that this state is getting repeated. Now, if this state is getting repeated and we are calculating it again and again, it doesn't make any sense, right? So what we can do is that we can store whatever value we have calculated somewhere. Okay. Now what were our changing parameters? We had two changing parameters, I and previous. Since we had two changing parameters, we can take a 2D vector to store uh, for each and unique pair of I and previous, whatever value we have calculated. So here comes the memoized approach. You see here, it's the same as the recursive approach, the workflow, everything is same. Just we are storing the values that we are already calculating. You see, we have declared a 2D vector here, and then we are initially assigning it to -1. That is, we haven't calculated it. Fine. Now, after doing this, what we do, each time we calculate the max of take and not take, we are assigning it to dp of I previous plus 1, because we are storing this in this particular state. Now, why are we doing previous plus 1? You see, in our recursive approach, we have started previous from -1. And dp of -1, if you do, it's out of bound. It doesn't make any sense. So, to make it valid, we are shifting all the indexes by 1. See, previous can range up to -1 to n-1, right? So this is the range for previous. So if we want to convert it to zero-based indexing, then we can just shift them by 1. We can convert them to 0 to n. Okay. So hence we will see, while we are declaring the size of our dp vector, for I, we are taking n. For previous, we are taking n plus 1, because we need all the indexes from 0 to n. Fine. Rest of the approach is same. If we have already calculated for this current state, that is dp of I previous plus 1, if we have already calculated, that is, it's not -1 anymore, then we directly return the value. And if we haven't, then we calculate it and we store it. Whatever we are calculating, we store it. Now, what is the time complexity here? See, the time complexity is big of n squared. Why is it big of n squared? Because we have n into n plus 1 states. N for I, n plus 1 for previous. And for each state, we are taking big of one time. You see, we are just taking two conditions. So it takes big of one time, and there are n square, nearly n square states. So the time complexity becomes big of n square. Now, what is the space complexity? We are taking a 2D vector which takes big of n square, and we are using recursion which takes an extra stack space of big of n. Fine. Now, you can convert it into tabulation where you will not be using this extra recursion stack space. Rest of the things like space complexity, overall space complexity, that is big of n square, it will remain constant, and time complexity will also be the same. Just you will reduce the extra recursive stack space. So you can do that easily. The concept is the same. You do that in your home. So now we'll be discussing a better approach. So what can be a better approach is that we saw that we got a space complexity is big of n square, that we are taking a 2D vector. So can we do this with a 1D vector? So instead of tracking that what are the possibilities starting from my current index, I can think of it like in this way, that what can be the length of the alias ending at my current index. Okay, so if we are considering ending at a particular index, what are the things that we can consider here? We can consider all the previous elements j less than I, because we are considering all the previous element. If that previous element is less than my current element, then I can extend that previous subsequence by 1. That is, we can take my current element and I can extend the previous subsequence value. Okay. Now, initially, we are assigning the dp to 1. Why? Because every element itself forms a subsequence of length 1. Okay, this is the minimum possible thing that you can get. You just take the element, it gives you a length 1. Now, the transition, understand the transition that we can take, if nums of j can come before nums of I, then we can increase the length of subsequence. So by how much can we increase that? Since we are considering this current element, we increase the length by 1. So suppose dp of j was having a value 5. That is the length of alias ending at jth index was 5. Now we are considering this particular element. Okay, so if you were considering this particular element, what can be the value? The value will be 5 plus 1, 6. Fine. Now, again comes the take and not take thing, because you see, we are doing max of dp of I or dp of j plus 1. That either we are not taking this element or we are taking that particular element. Okay, and then we return the answer, the max dp value, whatever values we are storing in our current um, vector dp, we return the max of those values. See, we are not returning the last index value or something like that, because our alias can end at any index. It's not necessary that it will end at the last index or something like that. It can end at any index. So we are taking the maximum value that is stored in our dp vector. Now, the space complexity here is big of n squared. Sorry, the time complexity here is big of n squared, but the space complexity reduces to big of n, because we are taking a 1D vector dp. Fine. Now, there is another better approach which takes very optimal space complexity and time complexity. Now, what is this approach? Suppose we are having this array. 20. Okay. Now, we track what is the smallest element that a particular length can end with. Okay, so why do we do that? Because for each and every position, if we take the smallest element that the particular length of our alias can end with, we can explore more future possibilities. Okay, because a smaller ending element always creates more opportunities for future members. We are not trying to preserve the current subsequence. Okay, we are just trying to maximize the future possibilities. Fine. So what we are declaring a tails vector, and what we are storing in the tails vector, the smallest possible ending of an increasing subsequence having length I plus 1. Okay. Now how this works is that if we suppose initially our tails vector was empty. Now if my current element is greater than the last element that I have in my tails vector, we just append it at the back. But if it's not, or like we have some element which is greater than or equal to my current element, then we replace that, because my current element is smaller. So anything ending at a smaller value will have more future possibilities. Taking that into account, if we ever find that in my tails vector, whatever we are storing, if my current value is less than or equals to some value in that vector, we just replace that. Now we do that using lower bound function. Now what does lower bound do? Lower bound gives you the the pointer to the element which is greater than or equals to my current element. Okay, let me show you the dry run. Initially the tails vector is empty, so you just append 3. Now we get the element 10, and there is no other element which is greater than 10. We just append it. Now coming to 1, you see we have 3 which is greater than 1. See, both the elements are greater than 1, but we need the first element which is greater than or equals to my current element, which is given by lower bound function. So when we get this 1, we find the lower bound of 1, so it returns the iterator to my position 0. So what we do is that we replace this 3 by 1. Because you see a subsequence of length I plus 1, see it is index 0, so a subsequence of length 1 ending at 1 is of course better, because suppose in future 2 comes, and if you are already having 3 in your subsequence, you cannot consider 2. But if you can take 1 in that subsequence, you can always consider 2. So keeping that in mind, we are making the choice greedily. Okay, so after getting 1, we just appended, we just replaced our 3. Now we get 5. Now what is the first element which is greater than equals to 5? This is 10. So we just replace the value 10. Now we get 20. Is there any value which is greater than 20? No. So we push the value 20. Now, keep in mind is that this is not the actual alias. In this case, it becomes the alias, but in certain cases, you will find that whatever you're storing in the tails array, it's not actually the alias. But what it gives you the length of the alias. That is the size of the tails array. Finally, whatever you get gives you the length of the longest increasing subsequence. But it is not necessarily storing the actual alias, actual order of the elements. Okay. Now, uh, let me explain the time complexity. Since you're using a lower bound function and it uses binary search, so for each and every element, you are using the lower bound functions which take log n. And for n elements, you're doing that, so it's n log n. And the space complexity is big of n because you are using an extra vector, that is the tails vector. So this was all about alias. Now moving on to longest common subsequence. Now in alias, we were dealing with just a single string, or sorry, just a single set of numbers. Okay. So in longest common subsequence, we will deal with two strings. Suppose A, B, C and S2 is A, C, D. What is the longest common subsequence here? A, C is the longest common subsequence. Okay. And if there are no common subsequences between two strings, we just return a 0. Now, how can you do that? Then we take the example A, B, C, and another string we have A, C, D. Now we will, in just a second. So initially we will start from the last index. Okay. So we will compare this index value and this index value. So since they're not equal, what we just do, we cannot decide, like if they're not equal, we cannot decide that whether to move this pointer backwards or this pointer backwards. So we try both the possibilities. And as I said, whenever there is a thing of trying out possibilities, you always use recursion. First, you see that what is the dry run of this longest common subsequence. Since these two characters are not matching, let me say that I'm moving this character backwards first. Okay, and there can be another thing that I have moved this character backwards. Now, this thing. Okay, so if I'm moving this character backwards, then we are checking C with C. C matches, right? If a character matches, then we move both the pointers backward. Since C is matching, we are moving both the pointers backward, that we are moving both to B. Because you see, initially it was at C, this moves to A and this moves to B. Now B and A, they are not matching. So again, two possibilities come. Either we can move this vector or we can this pointer, or we can move this pointer. So if I'm moving this pointer, then I reach the end of my current string. So I return a 0 because we didn't find anything matching after this character. But if you're moving this pointer, then my first pointer will be standing here and the second pointer will be standing here. So again, these characters are matching. So both the pointers will be going one back. So as we will see, the both pointers have reached the index less than 0. So whenever we are reaching an index less than 0, we just return. Okay. Now again, what will be the recursive function? Why did the test go? Now again, you need to find out what is the state of the recursion. What are the changing parameters? You see, we require two pointers, okay, to traverse through both the strings. So when we are requiring two pointers, so the state of the recursion will have two changing parameters, that is I and j, I for the first string and j for the second string. After getting this, what will be the transitions? Okay, the next step is transition. As in the example that I have shown you, when we are getting a matching element, that C and C was matching, we are decrementing both the pointers. And when they're not matching, we are trying two possibilities, that is decrement the first pointer keeping the second same, or decrement the second pointer keeping the first same. Okay, so there are two possibilities, as you can see here. Okay, here is the memoized code. Let me tell you the recursive code first. So when they're matching, what we do is that we return 1 plus recursion of I minus 1 comma j minus 1, because we have found one matching character, so we increase the length by 1 and then we recurse for the rest of the string that we have. Okay, and if we are not having the characters are not matching, then we return the max of two possibilities that we already have. What are the two possibilities that we have? That is recursion of I minus 1j and recursion of I j minus 1, because we are trying to move each of the pointers one by one and seeing that which uh, gives me a better answer. So this was the recursive code. So what will be the base case? Again, I said whenever both the pointers are reaching out of bound, that will be the base case. So whenever we are reaching out of bound, we will return a 0. That if my I becomes less than 0 or my j becomes less than 0, that we have completed, like the string has exhausted, then we return a 0. This is the recursive approach. Now, again, you will see there are overlapping subproblems here. There are multiple states which are getting repeated. Now, how can we store that? We can take a 2D vector because there are two changing parameters. So we can take a 2D vector and we can store whatever we are calculating for a particular index. So let's see the code here as you have. See, the base case is if both the indexes reach less than 0, or if any of the indexes reach less than 0, then we just return a 0. And if my current characters, like the pointers pointing to whatever characters they're equal, then I increase my length of common subsequence by 1 and I just uh, decrement both the counters. Okay. Now, if they are not matching, then I try out by decrementing each of the counters one by one. Okay. Now, since we are using a DP, each time we are calculating it, we are storing it in our DP. That is DP of index 1 and index 2. In whatever example we took, it is DP of ij, we are storing it. And if we have already calculated the value of my current state, that is I, and for a particular unique pair I and j, if I already calculated it, I just return it. I don't take the headache of calculating it once more because it increases my time complexity. Okay, so this is the code that if you have the value in your DP vector, you just return it. If you don't have the value, you calculate it and store it in your DP of ij. Okay, now we are initially we are passing the last character, last index value for both index 1 and index 2. I'm passing n minus 1 and m minus 1, that is the last index's value for both the strings, and then we are recursively decreasing them and reaching to 0, and finally we will get the value of what to say, the longest common subsequence between the two strings. Now this is the memoized code. What is the time complexity? You see, I can range from 0 to n minus 1 and j can range from 0 to m minus 1. So there are n into m states. For each and every state, we are taking big of one time. So the time complexity becomes big of n into m. And the space complexity is, since we are taking a 2D vector of size n cross m, so the space complexity becomes big of n into m, and we have an extra recursive stack space. Okay. Now this becomes the memoized code. Now coming to the tabulation part. As you have seen here, while calculating for a particular index, you need the value of the index before it. Okay. So when we are writing the tabulated code, we need to calculate from the smaller index, because for larger indexes, we are requiring the value of the smaller index. So what we do is that in our tabulated code, we start from 0 and then we go till the last index. Okay. You see, here the state dp of ij signifies is that What is the length of the longest common subsequence if we take first I characters from string 1 and first j characters from string 2? This is the significance of dpij here. Okay, now if see, initially our base case was if we are reaching out of bound, we are just returning a 0. But here, since we are like dealing with a zero based indexing, what we can do is that we can start our like calculations from index 1, and for index 0 we will handle the base case. If we don't take any value, I said that dp of ij means the longest common subsequence taking I elements from n1 s1 and j elements from s2. Okay, so if you're not taking uh, any alphabet, anything into consideration, then of course the length of the longest common subsequence will be 0. See, here j is 0 always. That we are not considering anything from string 2. So the length will be always 0. And here we are not considering anything from string 1. So the length will be always 0. So these are the two base initializations of our DB. Now then we start traversing from 1 to less than equals to m. Since I said that I'm like making the 0 based to 1 based indexing, okay, to handle the base case. So we are moving till n. But our strings, they are by default stored in a 0 based indexing. Okay, so to deal with that, each time we will be comparing index -1 and index 2 -1, because suppose we have reached index 1 equals to n and we calculate s1 of n, which is out of bound. So to deal with that, we will compare index 1 -1 with s2 of index 2 -1. Now you can think of it in this way, that I'm taking the first I elements and first j elements. So the first I elements will be from index 0 to I -1. So to account for that, we are comparing the index -1 elements. So if they match, then I increment my LCS value by 1, and then I check what is the longest common subsequence value that I've got in the from the previous elements, that is index -1 and index 2 -1. That is, if I'm standing at here, okay, I will see what is the longest value that I've got till here. The longest value that I've got is 1 because A was matching. So I will increment it by 1. That is, I'm increasing my length of the LCS by 1. And if they're not matching, then we take the maximum of, as you have seen in the recursive also, I -1 j and I j -1. Now we will understand it better if you see the tabulated version, that is, you see the grid. See, initially we are comparing these two strings. Initially, we have assigned 0, which is our base case. As you can see, this portion, that we haven't taken anything from any of the strings. So the length of LCS becomes 0. Okay. Now, if I'm coming to this index, okay, index 1, 1, you see that A is matching. Okay, since A is matching, what I will do, I will do 1 plus dp of index -1, index 2 -1. That is 1 plus 0. We will check the diagonal element. That is index 1 -1, index 2 -1. We will check the diagonal element and we will increment it by 1. So what we are doing, we are making it 1. 0 plus 1 is 1. Now when we are checking y with A, we take the max value of I -1 j, that is this value, and I j -1. That is, we take the max value of this cell and this cell. Okay, since these two are not matching. Okay. So this cell also has 1 because 1 is there on its right hand side, which is the maximum of these two values. Similarly for z also, we are since it's not matching with A, we are taking the max value of this cell and this cell. Similarly for x. Now the next value we have is x. Now x is not matching with A, so we take the max of these two values. Not matching with y, take the max of these two, max of these two. Now x is matching with x this time. So when our current element is matching, what we do is that we increase the length of our subsequence, that we do 1 plus I -1 j -1. So this is my I -1 j -1 cell. So I do 1 plus this. So I get a 2 here. Okay, similarly for other cells also you will see for this y and y they're matching, so I'm incrementing this 1 by 1. Okay, and this 2, see, these are not matching, but why is it 2? Because we are taking the max value of this cell and this cell. So in this way you will be filling up your entire dp grid. And where do you get the answer? You get the answer at the last index, that is dp of n comma m. Just a second. Now, here you see the last value that you are getting. This is your answer because here you have taken the complete, like dp of ij represented that you are taking I elements from string 1 and j elements from string 2. So this value dp of n comma n will represent that you have taken the entire string 1 and you have taken the entire string 2. So your answer lies in this last cell. Okay, so you just return the value of dp n comma n. This is your answer. So that was all about LCS. I hope anyone doesn't have any doubt. So Shubhrajit will be continuing from the next topic.
Hello, is my screen visible and voice audible? Okay, so let us start with the next part of dynamic programming. So these are not actually parts. What is this? Is a solving technique. Okay, so we will start with counting palindromic substrings. This is a form that I call as range-based DP. Why? Because in such problems, we deal with a range from some L to some R. And today we'll also discuss about another topic. Let me decrease the size of this, then it will be easier for you to see. We will also discuss about the topic of buy and sell stock. Here there is a normal variation of buy and sell stock, which you can all do, because today I'll be discussing about the two different type of variations, that is the cool down and the transaction fee variation. Once you know this variation, there are 5 questions on lead code of the normal form and you can solve all of them, and these two are also there in lead code, so you can solve that too. Let us start with the first question, that is the range based DP palindromic substring counting. Let us try to understand what the question says. The question says is, we are given with a string S and we need to return the number of palindromic substrings in it. A very straightforward question. What is a palindromic substring? Which reads the same backward as well as forward. For example, ABA, ABBA. You see, from this side also it is ABA, from this side also it is same. Here also from both the sides, it looks the same. So these are palindromes. Now, and also we know what are substrings, that is the contiguous sequence. There is no gap in between the sequence. Let us see the first example that we are given. The first example is ABC. Now, we always know that if there is only one single element, then it is always a substring. So I can always say that 3 substrings are surely here: A itself, B itself, and C itself. But no other substring in it. Let me consider AB, BC. None of this are palindromes. So our answer is just 3 in this case. And what are the 3 palindromes? A, B, and C. Now, let us see the example 2. Our example 2 is AAA. Here, again, we know that this one, this one, this one, these 3 individually are substrings which are palindromic on its own. But also, if I consider this 2 AA, or if I consider this 2 AA, and if I consider the entire string, this is also a substring which is AAA. All of these 3 are palindromes. That means we have a 3 plus 3, which is our answer, that is 6. Now, let us go for a generic example. Okay, suppose this example, A, B, B, A, B, B, A. Let me take this example. See, we always know that, let us skip two pointers. Okay, I and J. If I and J are on the same position, that means these are single elements. So whenever I equals to J, this means that my string has single character. And single character means it surely is a palindrome. That means such a substring will always return me true that it is a palindrome. Now, let us go to substrings of length. How much? Length 2. Okay, how do we do that? Our I is here and J is here. So we need to know that, is this substring of length 2 a palindrome? No, we can see this is not. Now we will check if something of length 3 is a palindrome or not, something of length 4 is a palindrome or not. So by our basic brute force approach, what we can do is, we'll have a O of n square loop to find all the substrings, right? Along with this, for every substring, we need a O of 1 function to check if this substring is palindrome or not. That means in total, our entire work will be a O of n cube work. And if I show you the constraints of the question, then see, it is up to 10 to the power 3. So 10 to the power 3 cube comes up to 10 to the power 9, but we can go just up to 10 to the power 8. So this brute force approach will give me a TI. Now I need to optimize this approach. For optimizing this approach, the thought of this is very simple. Let me tell you how. ABB, ABBA. Okay, now we always know what do we do in DP, that we break the problem into smaller subproblems and we don't repeatedly solve those subproblems. Fine. So what was our first question? That from L equals to 0 to R equals to N, that is this entire position. Tell me if this, tell me how many, or let us not take it as how many substrings it is. I will just ask, is it a substring? I mean, is it a palindrome from L to R? Now, I as a person, while coding, how I will think it to be a smaller subproblem? I will tell myself that, okay, at one step, I cannot tell that if this is a palindrome or not, but I can do one thing. I will just check these two elements, that is, suppose this is S. S of L equals to S of R. And also, I will keep a faith on recursion, that recursion, you go for me and you find the answer of this. This recursion will return me if my string S starting from L plus 1 to R minus 1, is this a palindrome? Is it a palindrome? This is what my recursion will give me back. So my actual answer will be S of L equals to S of R, and the recursion, sorry, recursion of S, L plus 1 and R minus 1. So what is it? That I will do my work and tell you if these two elements are equal or not. I keep faith that you go inside, check for this part, and tell me if this is a palindrome or not. If this part is a palindrome, so if this returns a true, and the starting and ending elements are also equal, that means my current substring is also a palindrome. If the middle portion is a palindrome, but these two are not equal, then this is not a palindrome. Or else the opposite case, that these two are equal, but the middle portion there is some error and not a palindrome. In that case also it will be false. So see how this question becomes simple after this idea, that we always know that memoization is easier than our tabulation. But here, the idea is so simple that we can even directly write the tabulation code. We do not need to even think about recursion, memoization, and other things. Yes, there is an approach known as, if I am not wrong, I have used it once. It is something as Manaster's algorithm. Maybe I'm writing the spelling wrong, but something like this, which uses an approach of going outwards from the middle and checking if it's a palindrome or not for the substrings. That is the most optimal method. But while learning about DP, we do not need to think about this. This method that we are using is also optimal enough for the problem to be solved. And as we can see that here we have two values. So we know that the state of DP will be a 2D DP. And what will this state represent? This state will represent that is the substring from L to R a palindrome. So if it is true, then we will increase our count. If it is false, we will not increase our count. Okay, so let us see how this state of DP is defined. And also from this, you can directly tell that it will be a O of n square approach, right? Because it is a 2D DP. Let us go to the code. While seeing the code, you will clearly understand that this recursive thinking that we are having is just for understanding. The tabulation is very easy to be written. So why we go on the road of recursion, then memoization, then I sit and think about tabulation, when we can directly write it. Okay. Uh, See, let me explain the code. Let me bring the picture there, and then let me explain the code. Right. That would be easier. Okay. Uh, okay. So maybe I'm not getting it pasted here, but okay, I'll take the screenshot and show you. Okay. So now let us understand it through the code, how it works. Fine. See, this is our length n, and then this is a vector, that is dp vector. Why did we keep one here during the initialization? Because you see that I always know if there is only one character, that is if I is equals to j, or maybe it is hard for you to understand for I and j, if L is equals to R, as we have explained, that means there is one character. So that is always a palindrome. So our initialization will be like this. Fine. Now, this is our count. How many substrings are palindromes? Why did I initialize it with n? Because I know the string of the length is n, The string of the length is n. If the length of the string is n, we know each single characters are palindrome. So at least n substrings I will have which are palindrome. Now I need to count extra how many substrings are palindrome. Okay. I find with every possible values of L and R. What do I do? If S of I is equals to S of J, which means suppose this is our string. I have just written these are characters. Okay, character 1, character 2. I will just check these two characters. If these two characters are equal, then I just need the answer of this much part. That is L minus 1 and R plus, L plus 1 and R minus 1. If this is a palindrome, then this entire thing is also a palindrome. You see, so if these are equal, so dp of I and j depends on dp of I plus 1 and j minus 1. If these are not equal, then no matter if this inside part is equal or not, this entire thing can never be a palindrome. So we instantly put a 0. What does 0 means? 0 means false, that it is not a palindrome. And finally, we do a count plus equals to dp. Why? If this is true, then it will be a plus 1. If this is false, it will be a plus 0. That means nothing is added. So this one is enough. And then we return the count. This is how easy questions are for range-based DPs. Always remember, in any range-based DP question, frame the question as L and R. That is, we have a long section of L and R where we need to find the answer. What you need to remember is, I will do only as much as I can do. In here, all I could do is check if the two sides are equal or not. Maybe in other question, the check is something different. Maybe it is an array and the sum of both the elements are even or not. You need to see that. So do whatever you can at your current step and then go for a smaller sub problem. Keep faith on recursion, that recursion will find the answer and bring that for me. And then I will join it with the answer that I calculated just now, and I will put it in my actual answer for the current value. Okay. So this is all about this ranged based question. Let us go forward to the next type of pattern. I hope the range based one was clear, and I have discussed the time complexity. The space complexity, obviously it is O of n square space complexity also because of this DP array. Okay, we have seen the DP array. If it was a memoized approach, still the space complexity would be O of n, but that would be a auxiliary space complexity. Okay, because with this we would have the recursion stack space. Recursion stack space is not considered in the auxiliary space complexity. Okay, so you can remember this in interviews, that if someone asks you what is the space complexity without the recursion stack space, you tell O of n square is the auxiliary space complexity, but the actual space complexity is O of n square plus the stack. Okay, in all types of DP problems where you stop at memoization. Now, let us go to the next type of problem. This problem is known as buy and sell stocks. BST. Okay, let me not write BST. You can think about binary search tree. So it's a buy and sell stock problem. With which one it is? It is with a cooldown. Now, let us first understand the question. That is, we are given a prices array. Okay, we have some price. Prices of I is the price of the given stock on ith day. We are clear with that. We need to find the maximum profit that we can get. And I can do as many transactions as possible. So there is no limitation on transaction. With one restriction. What is this restriction? Okay, let me clarify it. Transaction has two parts. Okay, it is buy plus sell, and also you need to remember that uh, you have to buy and then only you can sell. You cannot sell without buying. Okay, so this order should be maintained. Now let us come back to the question. What is the restriction? The restriction is that after you sell a stock, you cannot buy the stock on the next day. So this is like a cool down period. Okay, suppose I have bought a stock on the first day, I have sold the stock on the third day, then on the fourth day I cannot buy a stock. I need to buy it on the fifth day or not buy it at all. Okay, but at this one, just one day after selling, I cannot buy anything. Fine. And also, this is a note that you may not engage in multiple transactions. That means you cannot do a buy, and then a sell. You need to buy, sell this, and then you can buy another one, keeping 1 day gap. Fine. Now the question is clear to us. Okay. Let us see that we need the maximum profit. So here, at first only, the idea strikes in our mind that we have choice. That at a particular day, we have the choice to buy or we have the choice to sell depending on some restrictions. Okay, so every day we don't have the choice to buy as well as sell, but at a certain day we might have these choices. Now as we might have these choices, so let us see on the basis of what thing will we have these choices. Suppose we are on ith day. If we are on ith day and this is not a cool down day, not a cool down day, then on this day we can buy. If it is the ith day and it is a cool down day, then we cannot buy. Else in all other days, we can try to sell. Okay. This is all the idea you need to solve this problem. Now, how we will understand about this problem is again through the code, because these are kind of pattern based questions. Okay, if you get a template or what we call a blueprint of one of the problems, then you can solve 5 more problems. So always you should not think that I'll not see the solutions of a problem and all. If it is your first time solving any problem that involves this one, then it is absolutely okay to see the solutions, because this is the first time you're experiencing something like this. But once you know this solution, for any other question involving buy and sell stock, you should not look at the solution. Okay. Now let us see what happens in the code. Fine. We have the size of the array. We have the DP vector. Now you see this is a 3D vector. Why is it a three-dimensional vector? Because we have sorry, this is a two-dimensional vector only. It is not a three-dimensional vector. But why a 2D vector? Because it is not about just the ith day, but it is also about cool down. You see, while I was explaining the choices, what choice I have, this is a choice. This choice depends on two things, right? Whenever the choice depends on two things, then the DP state will have two values. If this choice would have depended on three things, then it would be a 3DDP, and so on. If n it depends on n things, it is a NDDP. So let us move forward again to the solution. This is our solve function we are calling, and it will give me the answer. Now let me see how we are sending this solve function. We are sending our vector that is given as input, the price. I'm sending the ith index, that is which day currently I am at. I'm also sending another variable, which is a Boolean variable, that can I buy on this day, which means this is actually my cooldown. That if it is a cooldown, then I cannot buy. If it is not a cooldown, then I can buy. So this value will tell me that at a certain day, do I have the facility to buy or not? And with that, I'm sending my DP array. See, initially, I'm starting with 0th index, and can buy, I am sending as 1. What does it mean? This means that as this is the first day, so I haven't yet sold anything. That means I can buy on this day. This is not a cool down day for sure. That is why initially we are sending 1. Okay. Now, if my index is greater than price dot size, that means I have gone through all the days. I can return 0 without thinking. Very clear. Now, what is this step? This is the memoization step. Simple memoization, that if I have already calculated the value of staying at ith day and having the choice of can buy, if it is already calculated, if it is not -1, then I'll return it. We have done memoization hundred of times. Then I come to a choice. If I can buy, that means not a cooldown day, then my answer will be maximum of going to the next day. See, minus prices of I. That means I am buying. So money is going out from my bank. So this is a minus of prices of I. What is the price? I am giving that price to someone. That means it is getting deducted from what I have. Plus, that is, I have done the buying on this day, and I have a faith on recursion, and I call it forward. That you go to the next day, but remember that now you cannot buy. Why can't you buy? Because you already have bought something and you didn't sell it now. You see, in the question it was mentioned, you cannot involve in multiple transactions. That means once you have bought, you need to sell before you buy another stock. That is why the moment I buy something, I make the can buy 0. That means I cannot buy. Can buy is false. And I send DP. Or else I choose not to buy. I'm not buying on this day. This is I am buying. Okay. This is I'm not buying. So I don't have any transaction. Nothing. No money is going out from me. So 0. Plus, you again go forward to the next day. But now you have the option to buy because you haven't bought anything today, nor you have sold. So it is not a cool down also. And no already bought stock is there with you. So next day you can go and try to buy another stock and you send DP. So out of buy and not buy, whichever gives you a maximum value, you store it here. But what if it is a cool down day? Now this is a cooldown, the else block. That is, I don't have the choice to buy. If I don't have the choice to buy, that means I have the choice to sell. So I will sell this stock. Why this is not a negative and this is a positive price of I? Because when I am selling the stock, I get back the money, right? It is added into my wallet. So this is going out from my wallet, that is why minus. And this is coming in my wallet, that is why it is plus. So by selling, I have got this money. And now I go forward and tell him, see, very important, that I do a I plus 2. What do you mean by I plus 2? That means I know that the next day I cannot buy. So I'll just skip one day and go to the day after today. And I'll tell that on that day you can buy, not a problem. Suppose I am on the third day. So there is no need for me to send it to the fourth day and tell that you cannot buy. Rather, let me direct send it to day 5 and tell that, okay, now you can buy because your cooldown is over. Another choice is, this is the sell choice. And why next is 0? This is my not sell choice. And if I don't sell today, that means I have the prices. I'll go to the next day to check if I'll sell on that day. Maybe I sell tomorrow. But still, as I have not sold, so I cannot buy anything. So can buy is still false. And I send the DP. That is all. So let us summarize the thing what we have understood. That is, if I can buy, the stock, then I will take the maximum between buying and not buying. If I do not buy, then I can buy in the next day. But if I buy today, then I cannot buy the next day because I need to sell. If I cannot buy, then I will take the maximum between. If I cannot buy, obviously I'll either sell or not sell. If I sell, then I plus 1th day, I cannot buy. If I cannot buy, then I will directly go plus to I plus 2th day, and here I can buy because my cooldown was for 1 day. If this question can be modified, how? Suppose they tell me that I will give you a value k days will be the cooldown. If k day is the cooldown, here I will directly go to I plus k and tell that here I can buy. As simple as that. The entire code remains same. Just in place of I plus 2, it becomes I plus k. If my question tells that the cooldown is for k days. Another one, that is this not sell part. If I haven't sold, then I'll go to I plus 1 to sell. I cannot buy till now and I cannot buy. Why? Because I haven't sold the current stock. Fine. Now let us move to the last question. After understanding this question, the next question becomes a piece of cake for you guys. Okay. Why? Because there is nothing extra in this question. The entire statement of the question is same. Just the restriction changes. That if the price, you are given a price and a fee, consider this as tax. You need to give a tax, okay? So for each transaction, you need to give a tax. So tax for transaction. Whenever you complete a transaction, suppose to a government, you pay some tax. Now, after paying this tax, you need to tell me what is the maximum profit. Here also the same rules, no multiple engagement and transaction fee is only charged once for each stock person purchase and sell. Fine. Now, let us see how this question is absolutely same with the previous question that we have done. There is literally no change in code except one or two lines. So for all the questions of this pattern, buy and sell stock, for all the question of this pattern, you will have a generic template. In that template, there will be change just on the basis of the restriction that is provided in the question. Whatever is the restriction, on the basis of that, you will make the change. So, how are you thinking about doing this question? We will understand this question also through the code. Why? Because these questions can be actually understood the best when you see the code of the question. Okay, so let me take the screenshot of this one, and you will see I have even tried to keep the variable names same as I used in the last question, uh, because of which it will be easier for you to relate it with what you have already done. Okay, so let us go ahead and see this question's code. We have the prices, we have the DP, same initialization, same solve function, everything is same. Okay. Oh, let me clarify in the previous question. If you haven't yet understood, it is a 2D DP. So time complexity O of n square, space complexity O of n square. But what did I tell? It's auxiliary. Fine. It will be same for all the buy and sell stock questions in most cases, if it does not become a 3D DP. Okay. So let us go forward with the code of this one. See, again, same thing. My ith index, can I buy? DP. And here one extra thing is fee. Remember, this is not a DP state, okay? This fee is constant. This is constant for every transaction you do. So we do not need a DP state for this. The same, first thing, I have seen all the days that I have, so I'll return 0. What is this? Our favorite memoization, that if this value is calculated, then just return it. Don't calculate it anymore. This is the main crux of DP, right? Now, the question comes, if I can buy today, then what I'll do is, I will buy, see, same, the minus of price, that is, money is going out from my wallet. I go forward solve, I go to the next day, and I tell that you cannot buy. Why can't you buy? Because you already have a stock, right? You cannot do multiple transactions, means multiple engagements while having one stock. As I told you, no buy, sell, sell, sell. So you have bought this stock, you cannot buy anything more until you sell this. What is the another possibility? 0. That is, don't buy. If you don't buy today, you go to the next day and you can buy on the next day. No issues. This is the else case. That is, we cannot buy. If we cannot buy, then what are the things we can do? I will sell the stock as I did before. This is my sell. Again, I'll go to the next day and I'll tell that, okay, now as you have sold the stock, you do not have any stock in your hand. So you can buy. You can buy a new stock. But you see, the entire code I have kept absolutely same. I have not changed one single thing except this one. One change in the entire code and you solve two medium level lead code questions. That is, whenever I am selling, that means one transaction is over. So whenever one transaction is over, you are getting some money in your wallet, but again, government is pulling some back from you, the tax. So give government the tax, no issues. When you buy, that time you do not need to give a tax because this is not the completion of an transaction. When you sell it, that time an entire transaction is over. You get some money back by selling, and then also you give some money from your wallet as a tax. Or else what you can do, this is the not sell case. If you do not sell, you go forward and you tell that you cannot buy. Why? Because you haven't sold me yet. You sell me and then you can buy the next stock. As simple as that. Entire code same. You just decrement the fee whenever needed. Same thing you'll get that when you have uh, buy and sell stock 1, 2, 3, 4, 5, they will have different type of restrictions, but the entire concept will be absolutely same. So here also, let us do a last summarization. What is that? Can buy will have max of buy and not buy. And this one's summarization is much more simpler. And cannot buy will have a max of sell, not sell. Here, just in this case, we will have a deduction of fee. That is, we need to give some tax. This was the entire concept. Here also, the time complexity is again O of n square, and the space complexity is O of n square. That means, what did we understand from this question? That for all such questions, we need to remember one single template, whereby closing your eyes, you can keep a can buy and a cannot buy. And then this line will depend only upon the conditions that is given in the question. Only this line will change in your entire code. Otherwise, everything is same. So today we discussed about the tax in buy and sell stock. We discussed about cool down in buy and sell stock. And we also discussed about number of palindromic substring along with the other topics like LIS and LCS discussed by Ishita. Okay. So that is all for today. I hope you liked the class and you have learned a few topics. See you in the next class.